Okay, good night, and yours truly, Dolphy Gilpin, coming to you from 1524 LaVista Drive, Decatur, Georgia. And tonight we're continuing with our CME. This time we are focusing on the second most abundant element in the earth. Previous occasion we had focused on the most abundant element in the earth, which was oxygen. And now we have silicon, which is the second most abundant element found in nature. Well, it's not found free in nature, but it's found in combination, in compounds of silicon dioxide, which mostly like sand, the sands on the seashore is comprised of silicon dioxide, which contains silicon. So it's not found really free, but in combination with other elements. It's also found in minerals, silicates, but we'll come to that. Now we had constructed two periodic table, which was derived from the magnetization property of our 5x12 matrix. And we said that our 5x matrix was extended to a 7x18, and to be more precise, because of the lanthanide and actinide series, which they have sort of make a special design for in order to constrict the width of the presentation. In reality, that it would have gone to a 7x32 in some cases if the lanthanide and actinide series was integrated back into the periodic table in the 6 and 7 period. So that was the thing that we had established and that we had described. So we had designed our first periodic table, which is here, which is sort of saturated with data. I don't know if you can see it here with atomic weights and atomic numbers and so on and so forth, and with the names. So there is more fine. So and this was the extension of the lanthanide and actinide with the 32 elements stretched out. And so this was an expanded view now, make it a little bit bigger, and we're highlighting silicon, which is in the 14th group and the third period. 14th group in the third period. Adjacent to it to the left would be aluminum on the 13th group, and to the right of it would be phosphorus, which is in the 15th group. Above it would be carbon, which is in the 14th group but second period, and below it would be germanium, which is in the fourth period and yet still the 14th group. And you will see it here, which is a little bit less explicit due to the finer writings. But like we said, we're focusing on this silicon here now, and we have put a little bit on the second periodic table of it in green because it has a little bit of health application there, both on the positive and negative side. We'll discuss that a little bit more. Silicon, which is positive and negative health effect. And it is a sort of paradoxical or ironical effect in that it is the second most abundant element in the earth crust, and it will be most abundant if it's combined with oxygen. When it's combined with oxygen, it's one of the most abundant compound in the earth's crust, making up about 27% of the earth crust. So by its abundantness, you probably would think it would have more health application, like its associate oxygen, which is the most abundant. But oxygen has a lot of health effect, but silicon is not found to have so many health effects. But let's us come to our application in with silicon as we sort of turn around this periodic table. If you turn on the periodic table here, I want to say now that we are CME.EE SLS, and you know that this was a topic that I discussed much in engineering. The SLS means serial-like sign relative to our AMZ5 construct matrix and the PEDM. But we were saying serial-like sign SLS, but why not say, because sand, wherever you have sand, you usually have silica, could have said serials-like silicon. Or sand-like silicon, or the reverse, silicon-like sand. Because wherever you find sand, you have silica, and it's found in silicon dioxide in most of the beaches where there's a lot of sand on the beaches. It's found there in silicon dioxide, and in silicates such as asbestos, granite, hornblende, feldspar, clay, mica. Those silicates are a source of silicon. So we have taken out a piece of the periodic table here. This is the periodic table, and silicon is represented here in the 14 group and the third period. And we have sort of taken it out, expanded it, and sort of focused on it here. So here are our silicon, and this is just a 14 group and the third period. So we're focusing on silicon now. 14th group, third period, adjacent to it is aluminum, to the right is phosphorus, below germanium, above carbon, and below germanium would be tin and lead. So that's the 14th group with silicon. The most abundant, or the second most abundant element relative to oxygen, which is the most abundant element in the Earth. As we said, silicon makes up 25 to 27% of the Earth's crust. And it is the second most abundant element, being exceeded only by oxygen. It is not found free in nature, but occurs in oxides and silicates. Oxides like sand and quartz and rock, crystal, amethyst, agate, flint, jasper, opal, and some of the other form of the oxides. Okay, we have drawn the structure of some of these silicon compounds. We have silane here with silicon here, and amide group there, methyl group there, methyl group, and metal group. That's silane, and with oxygen bonded there. Most of these bonds are like single bond on the silicon. Silicon is a tetravalent element. This is its Lewis structure, tetravalent. Then we move on to silanol, which is another compound of silicon. Silicon with some metal group and CH and oxygen there and that. Then we have silicon tetrachloride. Silicon tetrachloride here with 4 chlorine attached to in single bond to the chlorines there. Next we have what do we have? Trichlorosilane with silicon, hydrogen, chlorine, chlorine, chlorine. You have 3 chlorine, that is tri, and 1 hydrogen there. So we have silanol, silane, silicon tetrachloride, and trichlorosilane. Those are some of the compounds that we have silicons in. Now, as I've mentioned, when I've come on to some of the health application, it's a very few health application relative to oxygen that has a lot of health application. DBAS, which is dissolved bioactive silicate, is used for pimples and cuts and scrapes, sunburns, and so on. That is one sort of application for silicon there, the dissolved bioactive silicate. And we say now that DBAS, dissolved bioactive silicate, helps to dissolve toxin and unneeded substance from the body. So those are some of the positive health effects, direct health effect of this silicon. So one of the negative effects is miners who mine silicon and stone cutters, and after breathing a lot of the dust from the silicon mining and stone cutting, usually develop disease or abnormality called silicosis. And this silicosis is a very serious lungs disease that is called serious lung defects, and that's one of the negative impact of the silicon. All right, we'll next move on to the revolutionary application of the silicon, which is in the engineering field. And in the engineering field and technology field, this silicon is applied, first of all, in computers and cameras and solid state devices, watches, so on. But the revolutionary application is in the solid state device, MOS, metallic oxide semiconductor devices, field effect transistors, the transistor. So you have MOS, silicon MOS, silicon N and P MOSFET, bipolar junction MOSFET, unipolar transistors and bipolar transistors, all comprising of this silicon. So silicon is very intrinsic and to this semiconductor industry with solid state devices. Next, it is also doped with boron, gallium, phosphorus, and arsenic to control the electrical properties in these solid state devices. Though silicon is so revolutionary in this transistor industry that and the semiconductor industry that one place in California is named after it, called Silicon Valley. Yeah, Silicon Valley, where all the engineering silicon solid state genius thing resides in Silicon Valley, and they have sort of use up this silicon application to the point whereby the transistor has reached its limit in terms of the size or the constriction that it can really have. At one time, in semiconductor and the solid state device and integrated circuitry industry, they started off with some very large IC circuits and transistors, and then it was compressed or constricted till it got smaller and smaller and smaller and smaller and smaller and smaller, till they have reached the place now whereby they cannot make it any smaller, and therefore they are trying to look for other means whereby they could make it smaller. But the silicon has reached its limit in terms of the size of the circuitry it can project. They have tried in experiment the MOS or MOS2, something like that, the molybdenum disulfide. That's one experiment to sort of replace this silicon, but that is still in the development stages. This silicon has really made a revolutionary application to the earth in the transistors, MOSFET, JFETs, insulated IGBTs, insulated gate, bipolar transistors, and so on. Now, one of the other applications of this silicon is in this sintered silicon carbide. And sintered silicon carbide is a very hard substance. As you know, silicon is a sort of grayish, lustrous looking metal, or rather metalloid, not metal, but metalloid, which has both metallic and non-metallic properties, metalloid or semiconductor. And this sintered silicon carbide is second to diamond in terms of its hardness, and therefore it has application in making some very hard-tempered solid device, as they have made in the turbo car, this impellers in turbo cars, which make use of its very hard properties. There's also the HPSiC, or high pressure silicon carbide, and high pressure silicon carbide and this sintered silicon carbide are used to make very pumps, insulation pumps, and other devices. Now, there are other compromise of this silicon. We have like silicon, we have mentioned silicon carbide, we have silicon carbide MOSFET, we have IGBTs, which is the insulated gate bipolar transistor, which has its application in low voltage. We have also the SiNW, which is the silicon nitride tungsten field effect transistors. We have also, and sometimes they call it double SiN, which is the tungsten silicon nitride. Also, this nano wiring, which is the SiNW. NW can stand for the nano wiring, as well as can stand for nitride and the tungsten. And the silicon, polysilicon transistor, or poly SiNW, field effect transistor, has application in, also have some application in the medical technology field here, in its usage to diagnose bladder cancer. Yeah, this SiNW, which is nanowiring properties, but that is something to be investigated some more, as this is really just an introduction to our silicon as being the second most abundant element in the earth crust, and its relative position in the periodic table, and its comparison to oxygen, which is the most abundant. But as we know, oxygen is in what group? Oxygen is in group 16, and silicon is in group 14. And oxygen is in period 2, whereas silicon is in period 3. Now, about 7% of the body, the human body, consists of silicon. And that's one of the part of, in comparison to oxygen. This is like the second most abundant element, and the most abundant when it is combined with oxygen in the Earth's crust. And it has make up 7% of the body. It's found in bone skeleton, body fluid, and body tissues. And not much is known about its really intrinsic application to the human body. There's some application that is explicitly investigated, but it is said to be not known, and that more experiments and more research is needed to really find the full effect and the full application and the full importance of this silicon to the human. Now, we mentioned that in the engineering industry, it is doped with boron and gallium and phosphorus and arsenic in making other solid state devices which have controlled properties.